Things in the world have a lot of different properties, and we use units to describe them. Like an object's weight could be described in kilograms, pounds, ounces, or tons. Or size, volume, temperature, length, charge, brightness, and many more need to be described using units. Using units is essentially like multiplication. Imagine you have the unit of a hamburger weight. Let's abbreviate to HW. Obviously, one hamburger has the weight of one hamburger weight, whereas 2 hamburgers have the weight of 2 hamburger weights, and 2.5 hamburgers have 2.5 hamburger weights. But how many hamburger weights is a horse? Well, you could put the horse on a seesaw or a scale, and the hamburgers on the other side, and just count how many it takes to equalize. But then your friend comes over and says, "Man, this system is so stupid, we should use horse weights." Clearly, 1 horse is 1 horse weight, and 2 horses is 2 horse weights. What you'll notice is that the unit already has a certain amount of weight. A hamburger weight contains the weight of a hamburger, a horse weight contains the weight of a horse, and a kilogram and pound also contain a certain amount of weight within them. So actually, when you put a unit after a value, the unit doesn't just assign the value a property. It doesn't say, "Hey everyone, this number is weight." Instead, the unit itself contains the weight and is multiplied by a certain value to get the exact weight that you want to describe. This value is just designed to scale the kilogram value up or down in size. I think the easiest way to visualize this is using units of length. When we draw a centimeter, you can see it already contains a set length. If you wish to describe a longer length, you could combine 2 centimeters to create a 2 centimeter length, or 3 centimeters for a 3 centimeter length. Or maybe you actually want 3.5. Either way, it should be intuitive to you now that the unit already contains what it's describing, and the value that we place before it is simply a multiplication of this unit. That's also why all units are arbitrary. It's totally valid to use any set of units, kilograms, pounds, or hamburger weights. Although it's also clear that some units are easier to use in science or are more widely known than others. So for all of these units that I mentioned, they only contain some amount of something, like a certain amount of weight or length. But you could also include additional information in this value, like including the direction of the unit. When you're pushing a box, you're making it move, and to make it move, you need some force. The force is the amount of push that you give to the box. It makes a difference if you're pushing from the left side to the right, or from the right to the left. Now imagine you're pushing the box from above, and it's not even going to move at all because the floor is resisting it. So the amount of force that you apply influences how far you're pushing it, but the direction influences where the box is going to end up going. Weight, on the other hand, doesn't have this, because weight is distributed evenly across all directions. You may intuitively think that it's always going down because when you drop something, it falls down, or if you think of something heavy, you imagine it being dragged down. But the only reason it's falling down is because of the gravitational force that our Earth is applying to it. The Earth is applying a force called the gravitational force that is attracting the box to move down. It's not the weight that is making the box fall down, it's the force that's pulling it. So the weight of the box is an intrinsic property, meaning it's natural to the object and doesn't come or go. The box has a certain weight, and that's the whole story. But a force can come and go and influence its surroundings. A force will move things in specific directions, so defining that direction is important. That's why, whereas weight can be written as, for example, 10 kilograms, force can be written as, for example, 10 newtons to the right, or to the left, or downwards, upwards, or sideways. In fact, it can come from any angle. And none of these will have the same impact on their surroundings. The magnitude of the push will be the same, because the 10 is not changing, but depending on the direction, the movement of the box is totally going to change. So it's important to describe what direction the force is applied to for the math to make sense. Only this way will predictions using physics be accurate. All units have a magnitude, meaning how much of it there is, like 1 kilogram, or 5 kilograms, or 10 kilograms. But only vectors also have direction, like left and right. As a result, force is considered a vector, but the mass of an object is not. To denote whether something is a vector or not, it can be written with a little hat above it or with an arrow. We already mentioned that units already contain some value in them, and that we need to multiply them to get the exact value that we want. But now I'm going to explain to you what this is called. This is called a scalar, because it scales the unit up or down. In the end, I think these concepts are quite easy to understand. Units are constant values that we multiply to express some property of an object or our environment. If we find it useful to define the direction of the unit, it is a vector, and all units can be multiplied by other values called scalars to increase or decrease the amount of the unit. The most important thing is for you to be able to define the words vector and scalar, and if you can do that, then you're all set to move on to understanding linear algebra.